Hi, sorry for the wait. I finally got this mitochondria branch, and then there's its intensity and volume. I've modified this analysis program to a version that I personally find satisfactory. And it's in a state ready for you. So let's take a look at how C.elegans mitochondria are analyzed now. So it's essentially just a series of routines that analyze the local thickness of the mitochondria, then the volume of the mitochondria, intensity, and the bridge number, terminal number, and the junction number, etc. Alright, let's take a look in a moment at what that table will provide. Since these routines have already been written, all you need to do is minimize this window and leave only the run icon. Okay, let's bring it up first. Now, I'll open a few tools here first that might be needed during the inspection. The first is the threshold, which is located under Image Adjust Threshold. Once you click it, a small window will appear. Then another one is Brightness and Contrast, which is found in Image Adjust Brightness and Contrast. You can open it up. There's also another tool to synchronize the images later. It's under Analyze Tools. Synchronize Windows. So, what's the next step? Simply drag and drop our images. After you download the .lsm file, just drag it into the ImageJ. It will open. This is your raw file. Alright, next all you need to do is click Run. At this step you'll see a pop-up window appear. Now, regarding this step, I originally hoped that all the images could be processed with the same parameters, but I found that different C.elegans and their mitochondria image intensities are really not the same. So, this step is left to you, so you can define, based on the different images, exactly which areas belong to the mitochondria, and which areas do not. So, how do we determine this? First, I'll synchronize all the windows. At that point, you'll notice that, when I move along the z-axis, the two images move in sync, maintaining their z-section positions. Then, the area currently marked in red will be the mitochondria region we analyze later. So where do I focus? We actually focus on lines like this one, because in the raw data it should be connected. However, in this segmentation, in the subsequent binary setting, you'll notice that no matter which layer I pull to, it always gets disconnected. So, this indicates that our current parameters are too strict. Thus, the image intensities aren't able to connect properly. Therefore, in the threshold window, we need to lower this value. Right now, I'm using the scroll wheel to adjust it, while keeping my focus on this area. Ensure they can be connected together. After they're connected together, we need to go back and check again to see if this is in place, and if other areas have been over-selected. So, let's also adjust the z-axis a bit, and then align the images on both sides. They actually look pretty consistent. Once they're quite consistent, you can press OK. After that, it will take a little time to perform the analysis. Once the analysis is finished, it will soon close all the view windows. And then I'll pause it. Kill. Okay, good. Now, the log window on the right will tell you which file it's currently analyzing. And analyzing a file does take some time. The more mitochondria objects you have, and the higher the branch numbers inside, the longer it will take. But if there are fewer mitochondria, it might finish in about 4 minutes. However, if there are many, like in wild type where the branch numbers are very high, it might take over 10 minutes. During those 10+ minutes, you could more or less be studying, organizing images, watching shows, and then simply waiting. Now, let's take a look at the results. In the location where your files are stored, a subfolder will appear, and this subfolder will contain a lot of files. Let's check out the results I analyzed earlier. Inside this subfolder, you'll see many files. But what you really need to focus on is the composite and result files. Let's take a look. Now, here's how to review the data that you've analyzed. Since it's a 3D analytical result, I basically recommend using Imaris to display this data in 3D. Alright, let's start with the Imaris section. This is the interface you see after opening Imaris. This interface is called Arena. Inverse basically uses this interface for file management. So, we start here by adding an observe folder. And then you can designate the location where the files are stored. So, let's click on Select Folder first. Since I've already set it up, we don't need to do it again. The files are now here. In the previous section, I mentioned that among all these files, the ones most relevant to you are the composite files, and the CSV file that contains the results. So, let's take a look at the composite file. If at first when you imported it, it was a TIFF file, please double-click on it, and it will compute in the background and convert it to a file with the same name, but still as an IMS file. So, in the folder you'll see, in addition to the original TIFF file, an extra IMS file will appear. Then, the IMS file is a format that only Imaris can handle. Then, IMS files are the file format that only Imaris can process. Okay, then double-click twice. After directly entering this file content, you will see this image. It consists of 7 channels. Let me explain what these 7 channels are. I can first turn off the read line on the side. Let's start by looking at Channel 2. Channel 2 is raw FLE, which is essentially the actual image result of mitochondria. You can adjust the brightness of this image using the endpoint here. In Imaris, if you want to view it in 3D projection, you can switch the view angle here to 45 degrees. It will show a 3D projection, meaning objects farther away appear smaller and narrower, while nearer objects appear larger, so it gives a 3D effect. But since we're subtracting from our entire data, I want you to switch it to an orthographic view. That is, view it in a flat, 2D way. Okay, this is the first channel. You can directly rename the channel here. Rename it to raw image. So what is the first channel? If you check the first channel, you will see it's a very solid image. Let's rename it first. It's actually the mitochondria mask. This is the mask we created using Threshold in Fiji. If you return to the sliced view and turn off the raw file first, you will see the red areas represent mitochondria regions, while the black areas represent background. So whether it's the 2 volumes under our face, or the 2 bounding box intensities, mitochondrial branch, and the entire structural analysis are basically determined based on this mask. You might not understand why there are different color intensities. This is because if you look, when the mouse hovers at the bottom left of the screen, this area will show the intensities of different channels. At this spot, you'll see now that at this location, the intensity of the first channel is 82, at another spot, the first channel's intensity is 15. So this means, it's not only the mitochondria mask, but it also represents the mitochondria ID number, which can be correlated with our CSV file. This number indicates each analyzed object, so the index corresponds to these numbers in the first channel. For example, this is number 15, so you should correspond it to column 15. Okay, good. So this is the mask. After reopening the rodent file, you can check the mask you just created to see if it corresponds, whether it matches the raw image. Sometimes, if it's too faint you might not see it. You can enter one here, and it will fill all with the same color, so you can see it clearly. Now, the mitochondria that we just marked based on the recent threshold, they are already connected here. Alright, the solid parts have also been filled in. Okay, who's next to check? Next, we're taking a look at the 6th channel. At this point, I'll turn off the mask first, then leave the row down enabled, then switch back to the 3D view. At that moment, it'll turn on the 6th channel. And what about this image file? Because I've already processed it. So when it first loads, it should appear completely white. Alright, so this white appearance, you can switch it back to the 3D view. Then check whether the skeleton created using the mask actually matches what you had in mind. At least, I believe a skeleton like this fits my expectations. Okay, good. Now, given that the skeleton is completely white, it's actually very hard to judge, because we have already calculated its intersection points, as well as its terminal points and all its branches. So here, we can change the color of channel 6 from its original base color to the fire and map color. Okay, then you'll see. Now, within the 6th channel, I can first turn off the raw file. Alright, you'll notice that the orange represents all the linear segments of the mitochondria, which is its branches. Then the blue one is its terminal. Then the magenta color. It's exactly at the junction. Okay, so let's change the 6th channel to tag skeleton. Next, let's look at the 3rd channel. The 3rd channel is, according to this skeleton, help us find all the terminal points. So now I am selecting channel 3. But when the skeleton of the tag is removed, the blue dots should match each other. So channel 3 is our terminal point. Okay, let's take a look at what channel 4 is. Cyan of channel 4 is the location of junction. So it should correspond to, right above these purple positions just tagged. So it can be renamed junction. What is the 5th channel? The 5th channel. It is actually the position of the center point of each branch. In this mask, the center point location of its branch. How many did we end up counting? Then find out how many branches it actually has. So this is branch center. Okay. Then what the channel 7 is? Channel 7 is thickness. In channel 7, change it to fire. Then you can rename it as thickness. And similarly, this intensity can be adjusted. So you can take a look at the different display modes. So how do you display them? You should assign all your different groups to a proper intensity first. And then adjust these numbers. Alright, now it basically looks like I'm doing it this way, because after all, we wrote the program ourselves. So we need to check it this way. Our current program is whether the numbers on both sides are correct or not. Alright, you can check each file like this. But basically, I've already checked these 4 files, and they seem to have no major issues. Now, let's take a look. If you're interested in a particular string in the table, or a specific piece of data, and you really want to know exactly where it is in the image, what do? Let's select one. I'll first check that the file is correct. 17, DRP1, number 4, OK is good. So its numbers are correct. For instance, if I want to know this one, I want to know where number 2 is. Yes, where number 2 is. So you can create a new service here. Because remember, our first channel just now is our mitos. And it actually also carries information with an ID inside. So now, just at this spot, create a new service. The way to set up a service has been explained many times before. Also, on our YouTube channel, there's a tutorial, so you can rewatch it. Now, I'll quickly retrieve number 2s and show it to you. So after creating a service, the next step is to select channel 1 and disable smoothing. Then choose the absolute intensity. Because I now need to find number 2. So I have to set a range that includes number 2. I'll set it to 1.5 as my minimum value. And then set it to 2.5 as my maximum value. 1.5 to 2.5. Alright, if you set it from 1.5 to 2.5, then it will only include the image with number 2. That will include only the image for number 2. Make sure I'm on the correct channel now. The first channel. 1.5, 2.5, okay, then it will highlight it for you. Where we are now. With the image of number 2 in the table, and this pair of numbers on both sides, indicates where it is in this image. This is almost over. Alright, after it's done, I'll turn off the mask. Then we can adjust the surface. Here in the color palette, set it to be semi-transparent. Under the semi-transparent condition, maybe even fully transparent. We can turn off the roll data first. Now, let's take a look in the tag area. Then we can magnify it accordingly. So here we should measure it. 2 terminals. 1 branch without a junction. So we can verify that it has 2 terminals. And 1 branch without a junction. Okay, now let's take a look at the width of its bounding box, the height and depth, and also the intensity of its mitochondria, to compare them, to check if these numbers are correct. Okay, so after we click on this surface, you can find in the statistical results, in the details section, the specific value. Here you can find it. Let's start by looking at the volume. The volume is here, so its measured value is 11.380, and here it's a bit over 12. Now, the calculation for this is, because in Imaris, it actually uses a bit of interpolation, and our surface has undergone some smoothing. So, there will be a slight difference in the calculations, but since all our data are converted using the same scaling factor, I think that in this regard, this slight difference is not a big issue. Then, regarding the bounding box, we now need to use a box to enclose this 3D object. And along different orientations, what exactly is the size of this box? So, we can find the length of the bounding box here. So, the x-axis is 3.4, the y-axis is 3.4, then the z-axis is 6.9. Let's take another look. The bounding box, 3.4, 6.9, it's roughly the same. Similarly, the multiplier we use has a slight variation. So you might notice a slight numerical discrepancy. Okay, now regarding the image intensity, it's measured as 54.9. Then here, what is the measured image intensity? Because our raw data is now in the second channel, we need to look at the intensity mean of channel 2. Alright, 54, 938, so the numbers are correct. Okay, so, this thickness is measured in the 7th channel. So we need to measure the intensity max of channel 7. This, and the number you see here, requires you to manually add a decimal point, 10.00. So why add a decimal point? Because most imaging software does not support floating point operations. Meaning, if there's a decimal point in our image, I can't set it up for multiple channels. So you'll need to manually add a decimal point after the 2nd digit. Alright, looking at it this way, it seems like all our current calculations are correct. So you can run through each file and check. Then, if there are any other issues, we can discuss them further. Thanks for watching.